So let us start second day of our conference, and let me introduce Emily, who will take a keynote talk for today. Emily is a Brazilian physicist currently working as a research engineer in CNRS in France. And as she wrote, she is co-founder of the Cosmos Statistics Initiative and supernova collaboration, and some PI of several scientific subjects. As far as I understand, she is also working for LSST. It is a large survey synoptic telescope, which is not an which is still not in operation, but a huge work should be done before launch of the telescope to be efficient, to use a huge amount of data expected from LSST. And Emily is an expert in machine learning in astronomy, and today we will have a talk. She will have a talk about human role in machine learning, and the second part of the talk will be devoted to particular astronomical topics which might be interesting for all audience too. So Emily, please start your talk. Thank you very much for attending our conference. Thank you.
Thank you very much for the invitation, and thank you, Alexei, for the introduction. So, and before I start, I'd just like to say that I'm happy to be here. Unfortunately, it's not in person, but I hope that soon we will be able to have meetings in person again. I'll be very happy to meet with everyone. So let me share my screen. Okay, so for the talk today, I thought that it would be nice if we could. I think my camera is off for some reason. For the talk today, I want to talk to you a little bit about the role of the human expert in the era of big data, in the sense that um, I think that there is a lot to be, there is obviously a lot of data challenges that we have involved, but that we have to face. We have no option despite of facing them, because the data is too big and too complex. But in the end of the day, we want to do science with all this data, and doing science is an intrinsically human experience. So the human expert has a huge role to play in this scenario, and I'm going to talk to you a little bit about that today. So first, before I start, I would like to say that I'm here only speaking. All of the work that has been developed is done by people who are much smarter than me. Especially the work that I'm going to show with you today are developed within the Cosmos Statistics Initiative, the SNAD collaboration, and the Think Broker. All of them are international collaborations, mostly interdisciplinary, of people who are trying to see what can we do with all of this data that comes in our way. Specifically astronomy, because astronomy is what I work on and where I have experience of doing, but obviously the general ideas can be applied to any subject. Also, I would like to tell that my talk is divided in two very different parts. So I am going to talk first about supervised machine learning, and afterwards about unsupervised machine learning. And I'm going to stop in the middle to take questions about them, because they're very different subjects. So please feel free. In this meantime, I will stop, and then we can take questions on the first part, and then we continue to the next part. So starting, let's talk about supervised learning. So when we talk about supervised machine learning, what does that mean? I just wanted to do some, I know maybe this is very basic, but I just wanted to make sure we have a common ground and that we have the same vocabulary to move forward to the rest of the talk. So when I say supervised learning, this means that there is a training sample, means I have something to work on, something where the algorithm can learn from and then apply these things to something else. So there are many different ways of thinking about this. And one way that I think it's very interesting is that when we do supervised learning, we start with the hypothesis that the answer exists, even if we don't know what the answer is. Meaning, for example, if my axes are, for example, pictures of galaxies, and my y is the classification of those galaxies in spiral or elliptical or something else, there is a correct answer. So even if I don't know what answer that is, nature knows what that is. When we do any kind of physical or statistical modeling, what we are trying to do is to understand what happens in the nature box. So starting with the hypothesis that the answer exists, I have a picture and these pictures can be classified. I have a light curve and these light curves can be classified. So starting with that assumption, when we do some physical modeling, what we are doing is trying to explain what happens in the nature box. So I will try to explain what happened inside, and this is why I am allowed, for example, to um, discover things on Earth about gravity and make the assumption that the same gravity laws, physical laws, will function in another part of the universe, because I'm under the assumption that I'm trying to explain what happens in the nature box. And this is why I can transfer my knowledge from one experiment to the other. When you do algorithmic learning, you are not denying that the nature box exists, but you are not trying to explain it. When you do machine learning or algorithmic learning, you only recognize that there is an input, there is an output, and there is a map between the two. And you have no, there is no attempt to explain what is the physical process going on. We only want to make a map between the input and the output. And when in this situation, we should always ask, why do we think these things should work? Why, if I learn a map from one data set to the other, I have a data set with galaxies, pictures of galaxies and their classification, and I try to make a map between these two things. Why, if I take a completely different picture, why do I think this knowledge is transferable? And again, I'm still in the definition part. So what I'm calling here is representative. What the assumption is of representativeness, which means that for the sake of this talk, and I know this is a very, very simplified description of this, but just so we can be on the same ground, suppose that we have a mathematical distribution, right? So I have a Gaussian here, which is completely defined by a mean and a standard deviation, okay? So if I have a sample one, which is a collection of points, mathematically, I can also describe a mean and a standard deviation for this set of points. If I calculate this mean and standard deviation and that mean and the standard deviation, and I come to the conclusion that they are the same, I can say that the sample S1 is representative of this is mathematical that's probability distribution. On the other hand, if I have another set of points, S2, I also can mathematically describe me S2 and sigma S2, so the mean and the standard deviation. And if I come to the conclusion that this sample agrees with the statistical properties of my mathematical function, I can also say that S2 is representative of the probability P. In this sense, if S1 is representative of P and S2 is representative of P, I can say that S1 is representative of S2, which means that I can learn things from S1 and take my knowledge and apply that to S2 because they hold more or less the same statistical properties. And this is the assumption that we are having when we're doing machine learning. So when we're doing machine learning, we assume that my training sample, the ones for which I have labels, and I want to learn the classification for example, is representative of my target sample. So everything that I learn in my training sample can be transferred to my target sample. This is the hypothesis behind behind any learning experiment. This means that in the ideal scenario, the ideal supervised learning situation would be like this. You will have a training sample, a very big here is not in terms of numbers. Here is in the terms of content of information and coverage in parameter space, right? So if I have if I would have a training sample, a very big training sample, covered a lot of my parameter space, and this can be images, colors, light curves, or whatever we can measure plus classes. So for this one, I have the answer, and I want to apply that to a target sample where I have only the covariates, I have only images, colors, and whatever, but I do not have the classes. So in this situation, I can very certainly apply my machine learning to learn everything on the training sample and apply that knowledge to the target sample. So if I formulate this a little bit more uh, in a more mathematical term, what we will have is, for a supervised learning model, I will have a training sample, two data sets, a training and a target sample. I would have the set of all possible observables, so all possible samples, the set of all possible labels that I have, there should be the same for these both training sets, the training and the target set, and I will have a learner. A learner is something that will input my samples and will output my labels, right? And I will have a loss function that needs to be minimized at somehow. And behind all that, I have a data generation model that would tell me that for every sample comes from a given probability distribution. And my hypothesis that I told you before, that there is a true labeling function. So there is a function f that maps the x into the y, even if I don't know what that function is. And my loss function will be will be only how much do I lose if I am wrong. So what is the what happens if the estimation of my learner, which is the h train there, is different from the true value of the labeling function. And the important thing that I want you to, there are two important things I want to highlight in this slide. The first one is that this set of hypotheses is a machine learning model. A machine learning algorithm is only this one line of the H-trained learner. So it doesn't matter if you're doing deep learning or random forest or nearest neighbors or whatever. How you learn is just one line of the model, but there's a whole set of hypotheses that needs to be fulfilled before you arrive there. And representativeness is on top of everything else. So if you have all of this definition plus representativeness between your training and your target sample, meaning that the same probability distribution that generates your data are the same for the training and the target sample, then your machine learning model can work. So just coming back, if I have a very big training and a target sample like this would be the ideal situation. But what happens in astronomy is that the reality is something like this, because in astronomy, in order to have labels, you need spectra. If you need spectra, you have large biases on observation conditions, high signal to noise ratio, things that are very bright on the sky. So not only we do not cover the entire parameter space, but our training sample is absurdly biased in the astronomical situation. So this is just an example, so you can more or less see how this parameter space is different. This is a simulation, that's why I can show you these plots. But these are all data from supernova light curves, different types of supernovas, 1A, 1B and type 2s. And this is data from the first supernova classification challenge. It's a node one from 2010. This is just to illustrate how the parameter space is different. So here I have DES filters, GRIZ, and I'm plotting here the peak brightness of all the objects in my training sample in red and all the objects in my target sample in blue. So you see that there are entire regions of the parameter space that you do not have one example to learn from. And this is not going to change because we will never be able to get spectra for as far away for all the parameter space for which we have photometry from. So this will not change. For the specific case of supernova, there is, on top of everything, the problem that people like type 1As a lot, and they are very bright, and they are used for cosmology. So there's also a population problem. So you see here that the population of 1As in the spectroscopic sample for which we already have labels are much bigger than for the other ones. So this is a very known problem in machine learning. So this is not exclusively to astronomy or anything. So whenever you have this situation where labels are far too expensive, what we need is recommendation systems, and these recommendation systems, that they are used by many different scenarios. Okay, so for example, recommendations systems are used to do when you do drug testing for some types of drugs, when Amazon and Netflix recommend you a new thing to buy or a new movie to watch. What they are doing is they are using the information of your previous experiences in order to forecast what would you like. And also spam classification. So every time when you have a personalized mailbox, every time you actively click something as spam or not spam, you are helping the algorithm to understand what is spam for you, because that's different for different people. And here, obviously, I'm going to talk about the astronomical scenario. So when you have these situations of a very small number of labels and very expensive labeling tasks, as it is in astronomy, taking a spectra is super expensive. What we have, one of the options is to do active learning. You might know also this as optimal experiment design, which is basically the same thing in another language. But the idea of active learning is that you have an initial labeling function. You have an initial label pool, which doesn't need to be big. So you do just a few labels, and that's what life is. So you are going to take this initial training sample. You are going to learn a model from this, and then from this model, there's going to be a separation between class A and class B. You take this model and you apply to a completely unlabeled pool. So these are the unlabeled pool are the objects for which you do not have labels from. You don't know their classes. And within these objects, you are going to identify the object for which you do not have the label right now, but in case you had the label, it would be very informative for your model. So you are going to choose that one object, send it to a human or an observer, in our case, someone who will take a spectra for you, and then this information is going to go back to your training sample. You retrain your model and you do it like this. So what you are doing interactively here is that you are letting the algorithm itself choose the training sample, and then you avoid biases that naturally comes with a human making that decision. So when you do that, this is again a simulation, so you can have an idea of how it is. Figure of merit is something that supernova people like, which just it's a measurement between complete efficiency and purity. So how many of the objects that are there you classify correctly, and what is the contamination of your final 1A sample. So here is a very simple exercise, 1A, not 1A, and you just want this figure of merit to be 1. So if the highest, the better. What you can see here is that the canonical strategy is what happens if at every iteration you keep adding labels to the training sample, but you keep following the same strategy that we are following up to now, of very high objects that look like 1A, that are very bright, that rise more or less fast, and things like that. Passive learning means that you go to your target sample, you take an object to be spectroscopically classified, but you don't make any informative decision out of it. You just take a random one. And active learning is what happens when you make the conscious decision of choosing an informative model. In this case, it was a very simple uncertainty sampling. So I have two classes, 1A and non-1A, and in each iteration, I am choosing the object which is closest to the 50% barrier. Okay, this is very nice and very beautiful, but very idealistic. This is a simulation. There is zero constraints about how much telescope time I have and many other things. So in order to, when you make things more realistic, meanings when you add many different layers of complexity on this. So if you take into account the window of opportunity of labeling, because we would like to take spectra of things that are close to maximum brightness for classification. If you take the fact that your samples are evolving, so at each day your supernova will be brighter or dimmer, and this means that the objects that are available for you to query change. So your samples are not fixed. They change. They objects go in and go out of your samples all the time. The fact that you might have multiple instruments. So in this exercise, we consider 2 telescopes, one of 4 meters and one of 8-meter telescopes. And the cost of observing in those different telescopes are different. And also you have to take into account the evolving cost of the object, because not only you have different costs for observing these things in two different telescopes, but also these costs evolve, and they are different as times go by. So when you put all of these complications into account, the result that you have is that it does not matter if you are very complex or not. So what we did was we took this much more complex data scenario, taking into account all of these constraints, and we made the same exercise of using the active learning, but here we choose many different learning strategies. So we have different strategies for choosing what labels we are going to get next. And what we found was that first, the initial training sample that we have is super biased. If you start with the initial training sample that is already in the data, that is already there, which is focused on 1A-like objects, you spend more time trying to debias the sample than learning anything new. So you see that at each iteration here, the slope is not so big, because you are not learning much. You are just trying to debias the things that you have in your training sample. And on the other hand, if you start from zero, so you have zero bias in the initial training sample, it does not matter if you consider batch entropy, if you consider different types of information retrieval for each one of your samples. A very simple uncertainty sampling strategy works very well, because these much more complex learning strategies, they were built for very different type of data. So these much more complex learning strategies were built for Facebook data and Twitter data and stock market data and things like that, which are much more well behaved than the data that we have in real astronomical scenarios. So the lesson that we took from this is that for the complexity that we have in astronomical data, simple learning strategies still do the job as good as more complicated strategies. But everything that I'm talking to you right now is simulation. So how this translates into real data, right? So as I said in the introduction, I also work on LSST. So my day job is actually doing developing a recommendation system for the dark energy science collaboration. And for LSST, we have a big problem of the amount of data that we will have, right? So LSST is supposed to generate 10 million alerts a night. So what does that mean? You have the telescope. The telescope takes images of the sky and compares with an image that was taken some time ago. Every time there is something new, so in this example, there is some new dot there, this generates an alert. An alert is a very small piece of data that it sends to the community, actually sent to community brokers. LSST has just chosen 7 brokers that will receive the alert stream. And these brokers are have the task of taking this alert stream and filtering it and distributing to the community only the interesting ones. So, for example, the Think broker is the one that I work on, but as I said, there are 6 others. You receive the alert stream and you separate. This is supernova, this is solar system, this is a variable stars, and you direct those streams to the users that are interested on those type of things. For the Think broker, we have specifically an early supernova classifier that takes into account everything that I told you before. So in this sense, LSST is not ready yet, so it's supposed to be ready in 1 or 2 years. But now we are working with ZTF alert stream. So in order to test our systems, we are working on ZTF, and we are already reporting the candidates we find to TNS. So we started with 20 randomly chosen objects, 10 of each class. So you have 10 1As and 10 non-1As, and you run it through 40 iterations of the active learning loop, as I told you before. And then this final model is implemented in the Think Broker. At this stage, this classification process is done on catalog data because we are still negotiating how the spectroscopic follow-up will follow. In the future, we will make that a more live thing, but we can talk about that in the questions if you want to know more about that. At this moment, we have a model that was trained after 40 iterations with using everything I told you before. And this trained model is implemented in the Think Broker. There is a few other issues that it needs. We have another deep learning classifier. They both should agree, but they agree like almost all the time. And we have a cross match with known objects. So we filter out things that are there, but they are already reported or already cataloged in the literature. We have been doing this since November 2020. So these numbers that I have here is from November 2020 to March 2021. So during that period, we reported 310 candidates to TNS. Among them, 205 were classified as 1A, and 168 of them were confirmed to be 1A. Of course, we have to be very careful about these numbers. There is the caveat here that this is not a complete sample. So we report to TNS, but we have no way of controlling who takes a spectra of what. So most likely all of these things, a human is still look at the light curve to make a decision if they are going to take the spectra or not. So we should take that with a grain of salt, but it's a good at least it's encouraging that the results are good for this point. So just to finish this first part of the talk, if you have to forget everything that I said, I just want to highlight that we should build recommendation systems specific for the targets that we want to target. So, for example, this example that I showed you is 1A just because I am involved in the 1A community. But if you are looking for other types of transients of other type of objects, it is very important to tailor our classifiers to the things that we are working on. And for the most complicated scenarios that I was talking to you about, there are caveats in using machine learning, and we should avoid off-the-shelf algorithms because they will not work on astronomical data. Our data is very, very different from the data that are normally used to the development of machine learning methods. And this is why it's very important, not only that we are conscious about what kind of machine learning we are using, but also that there are interactions between the astronomers and the computer science people developing these models, so we can better describe the data situation and say what exactly we are looking at. So this is the first part of my talk, and I would like to stop here because the rest is going to be very different. So if you have any questions or comments on this part, I would be willing to take them now.
So, dear listeners, please generate your question, and we have approximately, I would say, 5 minutes for questions and answers. Okay, why you are generating some questions? I'll ask Emily. Emily, you talked about brokers in LSST, and my question about possible errors in brokers. So there's a positive false and negative false. What do you think about these errors which your broker will send data and candidates? Which kind of errors you would like to avoid during classification of candidates?
Yeah, so there's always going to be some kind of error which is unavoidable. We have many different filters that we try. Okay, let's put it like this. There is a balance there between trying to filter out the errors and filtering so much that you lose some interesting objects. So this is a choice that we have to make. For example, each broker makes those choices differently. So for example, in Think, we are very conservative in the sense that we have very high quality cuts for the points we report as observed. Uh, but we also report a different set of points that we say, well, this was sent to us by ZTF, but it did not fulfill our quality cuts. So all of the classifiers, the way Think works is that each module is different by the community that is going to use it. So you can choose if you are going to use the points that didn't pass the quality cuts or not. Most of these classifiers, and I think I don't have the plot here, but um, um, the majority, especially for this Think module, we see that the majority of the non-classified things are like AGN-like things or variable stars, because there are many in the broker among the decontaminations that we have. We are trying to make them as low as possible, but as I said, at some point we have to choose. Otherwise, we also start losing very interesting objects anyway.
Okay, but it is obvious that some object could not be classified at all. So
Mm-hmm.
it is so-called unknown. Do you
Yes.
foresee a lot of unknown or non-classified events, and
Yes.
how can reach how to practically how we can reach? I mean, audience
Yes.
scientifically can
Yes.
reach this unknown. Mhm.
Yeah. So actually, the unknowns are the largest class that we have.
Yep.
Yeah. So the majority of what we have are unknowns, and one of the interesting thing is that we don't have many people interested in them.
Why?
So, uh, yeah, I don't know why, but if you are interested in the unknowns, we should have a minimum criteria. For example, what is the range
Ah.
of magnitude you're looking for, or what is the sky position that you are looking for, or things like that. But it's very easy to make a filter in that sense and send you only the ones that pass through these minimum filters that you have. That is very possible to do. We just don't do because nobody asked, basically.
Okay, and one more question about filters. About do you have a filters for a candidate to afterglow gamma ray burst?
We have one. I am not sure if it's in production yet, but yes, we have one that was very recently being developed. If it's
Mhm.
not there yet, it should be very soon. But
Mhm.
I would like to stress that these things, one thing, there is no problem in having two different filters that work intrinsically different algorithms. That's fine. I don't think
Yeah.
that's a problem. And so if you're interested, it's very easy to, especially depending on the requirements that you have for your filter. So in Think, the module it's basically a function that inputs something and outputs the classification. But if you have a few filters that can allow us to downgrade the volume of the stream, because the problem is the volume of data. So if we have magnitude cuts, or as I said, right ascension declination cuts, or things like that, that allows us to make the stream smaller and then easier to forward to other people.
Mhm.
But
Okay,
that's
thank you.
doable. Yeah.
Thank you for answer.
Um,
So, mm, uh, is some any more question? Please don't hesitate to ask any dummy question, because it's just popular lecture just for understanding of basic principle of machine learning, and
yes.
especially for LSST, it is just a particular question, but other part of the talk was
Yes,
general.
sure. Uh, so I am going to continue now because we are running time. But if you have questions, you can put them on the chat, or you can ask in
Okay,
the end, and
great,
then we
thank you. Please
can,
continue.
yeah, we can continue. Okay. So everything I talked to you about here, it was up to now was about supervised learning, meaning things for which we do have a training sample and for which we do have something to learn from. And if you remember that I talk about the nature box, we are under the hypothesis that the nature box exists. Okay. So I am going to go to the second part now, and I'm going to talk about unsupervised learning. And unsupervised learning is a very, very different situation because it's not a mathematically well-defined problem. So if you remember, um, that I told you that the in the beginning of my first hypothesis, I said that the answer existed, and in unsupervised learning, we are not gonna have that answer anymore. So what is exactly that you are looking for is also one of the parameters that you yourself as a user has to write. So just to I am going there are two basically types of anomaly of unsupervised learning, which is clustering and anomaly detection. And I know this is a simplification, but it's for it's for the sake of this talk only. Clustering, you are trying to find groups within your data, even though you don't know exactly what these groups are, but you know that they seem to be similar to each other. And on the other hand, you have anomaly detection, which is you are trying to find things that are unusual or unexpected in your data set. So an anomaly basically is an observation, according to this definition, is an observation which deviates so much from the others observation from the others to arouse suspicions that it was generation by a different mechanism, right? So you can have outliers or point anomalies, for example, where you have a group of things and then you have a few points that are different. You can have time series anomalies, for example, if you have time here and the y-axis, which is anything. This type of the time series will have an anomalous behavior, for example, or you can have group anomalies. So you have groups of objects in the input space that they behave, looking at the only in the input space, they behave more or less the same. But when you go to when you look at them as a group, they have very different statistical properties than the other group. I am going to talk about the first point here, which is anomaly detection for isolated sources. Okay, and when you talk about this, we do have to think about that the definition of anomaly is intrinsically connected with the social environment that it is the current state of the art of the scientific knowledge in that field, right? When I say that an anomaly aroused the suspicions that it was generated by this different mechanism, as a scientist, what we ask is, what is the different mechanism? Is this something familiar, or is something that we should have known but we fail to recognize, which would be an important information as well? Is it something that we have never seen before, and is there something new for us to learn from these anomalies, right? um, and in order to but in order to identify what is usual, you need to have. I'm sorry. In order to identify what is unusual, you need to have a clear idea of what is usual. What is the bulk of your data? How your normal data look like? And that is a social construct, and it changes with time. So I deeply there is this book which I find very interesting. It's called Discovery and Classification in Astronomy. It talks about the history of astronomical of very different weird things that happened. One of them was basically it talks about when did the Earth became a planet, or why did Pluto was a planet for so long, and why people were so sad when it didn't when it was demoted. But it's the important thing to understand here is that in order to understand what is unusual, we first have to understand there is the not the state of the art of knowledge that we are inserted in, and that is something that only a human can do. So machine learning in this sense, machine learning can only produce recommendations. And from now on, I am going to talk specifically about the work of this NAD group, which is a collaboration that we have between France, Russia, and the USA, that we started like 3 or 4 years ago, specifically looking for anomalies. So what is going to be the pipeline here? So I have an anomaly detection algorithm. For example, in this case, it was an isolation forest. We observe the data set. we identify potentially interesting anomalies. So we have a list of anomaly scores. You send that to an expert, which is a human, which will tell you this is not interest, this is kind of interest, but everybody already knows about it, and things that are very interesting. Then you should get more data or publish or try to understand better what is happening there. So just for a very, very simple implementation, we use an isolation forest algorithm, which is basically a decision tree where instead of trying to focus on what happens on the leaf nodes, we are looking for objects which are very quickly isolated on the tree. So if this is a completely randomized tree, so the features are random and the decision points are chosen at random. So we are under the hypothesis that an object that is isolated in parameter space will need less number of splits in order to be left alone in a leaf. Using that kind of algorithm, we applied this to ZTF data release tree, which was expected to contain mostly stars and periodic variables. So this is more or less what are the things we would expect to find on ZTF DR3. And we found, using these things, we found a lot of artifacts. So most of the anomalies that we found, they were actually artifacts, which are things that are different. So they are statistical, from the mathematical point of view, they are anomalies, but they are not scientifically interesting because they are like satellite tracks or bad CCDs or ghosts or uh, effects of other things that we know there should not be there, but anyway, they were there and they are not scientifically, astrophysically, nothing new to learn from here. But the interest that we found, and this one was a super interesting one that we found as well. So here we have a variable star in the front, which is in the middle, and you see the huge behavior of the variable star. And in all of these points here, you see the ghosts of the you see light from things that are behind or in front of, I don't know, of this object. But this variability that you are seeing is not from the secondary sources, it's actually from the main source that we have. And we also, you probably know this already, because we also find some hints of the Barcelona asteroid that was passing through a source, and it was caught as a transient in the database. So this is just to tell you more or less of the things that we found looking at ZTF DR3, but that are still very high incidence of anomalies, of artifacts. As I told you, like 68% of what we found was not super interesting. And what we want is to maximize the number of scientifically interesting anomaly that is shown to the expert. So if you think that you have millions of things in the data set and only a very limited number of human experts who can look at it, the only way that you can do that is to incorporate human knowledge in the machine learning model. And what we are going to do here is just close this loop. So once the expert tells you this is not interested, this is interesting, this is very interesting, you take that information, you put it back into your algorithm, and you update the algorithm. In the case of the, I'm not sure if I have here, yes, in the case of the isolation forest, what happens is you take the object with the highest anomaly score, and then you apply that and you show that to the expert. If the expert tells you, yes, this is interesting, then you do nothing, because the model is working as it was supposed to be. If the expert tells you this is not an anomaly, you are going to go back to your isolation forest and change the weights of the decision path that led to that anomaly. So you are going to downgrade that decision path in a way and recalculate all the weights of your forest in a way that now the anomaly in a way that now the expert reply will be included in your it will be included in your news course. I think there is a question.
So I would prefer to have a question after your talk, if
Okay.
possible.
Okay,
Okay,
good.
please
Okay.
continue. Okay, thank you.
Okay. Okay, good. So this is what more or less. So as I was saying, we changed the weights of the decision, or the weights of the trees, and then with this new updater, you do it again, and you ask to the expert again. So this is basically more or less the same idea of I was talking to you about before, but now for applied to anomaly detection algorithm. So we first do this in a very small data set. These were like 2,000 light curves from the Open Supernova catalog, and you see that here uh, on the x-axis, you have the number of candidates that were presented to the expert, and the y-axis here are the fraction of true anomalies that were confirmed. And you see that in blue, you have a random sampling. In orange, you have an isolation forest. And on green, you have the active anomaly detection results. So when you actually actively ask the and put the feedback of the expert back into the algorithm. So when you look at the order of these things, you can see that what happens is this plot is the name of the objects that were found. So the upper branch is the normal isolation forest algorithm, and the order of anomaly score of that come out of that algorithm. And on the bottom, you have the objects that were presented to the expert by the AAD algorithm. And the interesting thing to have is first that in the beginning they are all the same, because the first iterations, they are all a normal isolation forest. There's no difference of this. And you see that the most anomalous object, remember, this is the Open Supernova catalog, so there should be supernova things in there. And the most anomalous object that was in this catalog was a binary microlensing event, a Gaia event. And in the isolation forest algorithm, it took like, it was in number 33 in order of anomaly score. And in the active anomaly detection algorithm, it was the first one that was presented to the expert, and at number 14. So it was found much earlier, and beyond that, you can see that there are much more concentration of true anomalies in the later queries for the adaptive case than in the normal case. So although there is this initial phase of burn-in that the algorithm is trying to understand what is an anomaly or not, for the specific definition of the expert. After a while, these things kind of concatenate, and it starts to getting things better more frequently. And we also did this, and we did the same idea, and we applied this to ZTF data. I don't remember the number, but there was a lot. The orders of a few thousand, 100,000 of objects in that data set. Um, I think I don't remember exactly the name, but it was a very large data set, and we found at this point we have 159 newly discovered transients. From these, I think around at least half of it were found with the active anomaly detection algorithm. And this is interesting because this data set should not have, and we even found transients that were not reported in the ZTF alert stream. And everyone that we talked about this that were used to this data set said that there are no supernova-like objects in the data releases, or very, very, very small number. And we ended up finding things that are there, which was super interesting. So the take-home message that I want to give you here is just that there are two very important things that we need to think when we think about discovery and application of machine learning algorithms in large data sets. The first is that if you're looking for discovery, serendipitous discovery will not happen. In LSST, we will not find things we're not looking for. That's not going to happen, because with 10 million alerts a night, it is impossible that we will randomly bump into things that are interesting. That's definitely not going to happen. And the second thing is that I would like to stress the very important decision strategy that we made on SNAD from the beginning, from our, I cannot say that was completely planned from our part, but ended up like that, is that domain experts, in this case astronomers, should be included in the development of the first stages of the algorithms, because they are the people who will tell us, who will tell us, and I mean the people who are developing the algorithms, what to look for, what is important and what is not. And in the end, a discovery depends on them. And in that, I have to deeply thank the work done in the ISNAD team, not only from the development part, Matwei, Vladimir, and Kostya, who did an amazing work on developing the pipeline and the viewer. But I would like to especially highlight the work of Maria and Alina, who went through a lot of those candidates and actually guided all the development of those of the pipeline that we had there. There was a super important, and I think in our case it was not absurdly planned from the beginning, but the more we discuss and the more we think about it, the more I am convinced that in order to find things in ZTF, it's absurdly important to have people doing this work that they did, that Maria and Alina did, of looking and guiding the people developing the algorithms, telling them what is important, what is not, and trying to input domain knowledge into whatever comes out of our algorithms. So with that note, I would like to thank you a lot, and I would like to think from the title of my talk. I started off this talking about the role of the human expert in the era of big data. And in the end, after everything I said, I cannot tell you anything different than that the role of the main expert is to define what is meaningful. And that is something a machine will never be able to do. And that's why we deeply need to strengthen the collaborations between the astronomers, the people who know the data and who know the astrophysics that is going behind that, but also and make them work in partnership with the people develop the algorithms. And I know this is not a new idea, and I know that this interaction is not easy. It's very, very, very difficult to, especially in the first stages. There's a lot of jargon and a lot of patience that is necessary. But I think this is especially important if we are going to find anything that we are not looking for in the middle of LSST data. So this is what I had to talk to you. Thank you very much. And I will take questions if you have them.
Emily, thank you very much. And we have empty time for questions. So please, questions, please. Okay, so while somebody would like to ask more, I mean, questions. So I ask you, Emily. So you think you said that the role of the human expert is to define what is meaningful. So my question is, should we define what is meaningful before or after machine learning, after training, machine learning, and so on? What is the role definition before and after?
Yes, this is a very, very good
question. I have a lot more questions.
This is a very, very good question, and I think and something that we struggle a lot. So let's. I think my question, my first answer for that would be, start from something you know. So start from something, and then open little by little your definition of what is an anomaly. Because for example, if you are looking for supernova, you can, okay, let's look for transients, which is a little bit more broad. But then you have we have the problem, and this is a problem that is highly discussed in all the community that works with anomaly detection in astronomy, is that, okay, I am looking for these weird things, I found these weird things, and then I look at that light curve and I don't know what to say anything about it, because I am not an expert in that field. I have no idea if that is important or not. So I think my strategy, the strategy that I think it works, is take a group of experts that are willing to take the patience to work with you. Make a first module on something that they know about, that they can advise you about, and then afterwards, in the subsequent steps, you little by little enlarge your definition of what is interesting or not. Because if we start with some very, very broad things, It's very difficult even for the expert that is working with us to understand if that is meaningful or not. At some point, I do hope that we are going to be able to find things completely that we have no clue about. But I don't think that will be in the first years of the survey. I think that will take a while.
So in this approach, you expect some discoveries after.
Yes, yes,
Yeah, great.
definitely.
It was the idea of my question. So
Yes.
second question, if possible, what is the mechanism of some statistical confidence in machine learning? So it's a big problem.
Yes.
Do you have some idea how we can estimate statistical significance and predict
Yeah.
even predict statistical significance because we do not know real distribution,
Hmm.
so we have no idea how we can work with probability density. So
Yes.
what is
Yes.
the approach in that topics which you are discussing
Yes.
now?
Yes.
Thanks.
So there are a few. This is a very good question, and this is a point that has been highly. Let's put it like this. I know that this is a question that is highly discussed among the scientists using machine learning. I am not sure if this is a question for the people who are developing the machine learning algorithms, because these two people don't talk. So when you talk about, I have already had very weird conversations about people who are highly in the development of machine learning algorithms, pure computer scientists, non-astronomers at all, and the idea that they have about what is an error in an observation is very different. They even, for example, if you are looking for estimations of errors in the prediction, that might be because there are some Bayesian neural networks and things like that that you can use to estimate more or less. It's not a probability, but it's something that they call a probability for the output of your data. The question of how to deal with errors on the input of the data, that's much more complicated. I have seen one or two options of people trying to do that. They end up with some kind of hierarchical Bayesian model where, for example, if you have a tree, for example, you propagate the probabilities through all the nodes of the tree, and in the end, you would have a probability. But that thing is absurdly computationally expensive. So even if it works, you cannot do that for too many data sets because like computationally is very, very, very complicated. I don't know, I don't have a defined answer to your question, but I do think if you have a computer science friend, it's something you should definitely talk about because this is super important. I agree.
But I agree that my question has a meaning because any kind of prediction or any kind of statement should be supported by probability.
Yes, that's true. So
So,
for example,
sometimes it is not enough to say, I see my eyes that it is a supernova.
yes, yes, I agree. I agree. So if you think about that sense, in that part of the, for example, when you use when you use a forest, for example, to make your decision, what people do is you you do a statistics of the replies of the forest, right? And this gives you kind of a probability. So if 50% of your forest or of your trees in the forest says that it's a type and 50% says that it's another type, you consider this a 50% probability of being one way or the other, for example. So it's almost like the frequentist way because you randomize the input. So you randomize the features and the decision paths that you have. And then in the end, you do the same thing many times and you have a distribution. So you kind of, um, they kind of use this as a probability of being of one type or the other. In deep learning scenarios, I have already seen people using, for example, randomizing the outputs of the nodes or taking out parts of the nodes and things like that to try to make a statistical distribution of the results. This is possible, and I think at some point this is okay. What is more difficult for me is how to what I was meaning was that how do we propagate the uncertainties that we have in the input? That I have no idea if machine learning people are dealing with. So in the estimation, I think there are a few attempts, and It's not mathematically completely okay, but it works for all practical purposes. It works, but for the input part, I think it's a more complicated point, because all of these machine learning models have a billion parameters and propagate through all that. It's super complicated.
Okay, what you think about Monte Carlo simulations input flow with known parameters, just to understand output parameters and estimate the method, the quality of the method? What's your idea? Because in this way you will know initial distribution and will obtain after so-called training sample, and you obtain sturdy output. And
Yes.
you could compare the propagation of errors or
Yes.
propagation distributions from your method.
Yes. Yes. But
What do you think about that?
yeah, that's a good thing if you completely believe your model, right? Because you have to believe the modeling that you are doing for the in the case of the generative model, you have to believe the likelihood that you are using to generate those things, and you have to believe even if it's a simulation, you have to believe the simulated model that you have to generate to forward model those things. So if you believe on that, then that's fine. For the specific case of astronomy, I am not sure if I believe on that part of the modeling, but if with the hypothesis that we are assuming that part of the modeling is okay, then I think yes, it's a good, interesting way to explore the parameter space. But again, you are only exploring the parameter space of something you know, because you have to input the model in.
Okay, thank you for answer.
Yeah.
So I see that some question arised. So who will next? Sergey Stupnikov, please.
Yeah, I have a couple of questions. So the first one is, so Emily, you mentioned some concrete machine learning method that you applied in your subject area, but could you please keep it more explicitly? What are the most applicable machine learning methods right now in your subject area? Could you enlist them?
So there are a lot. Okay, so most of the things that are done are based on different architectures for deep learning. I'm talking about photometric supernova classification, which is the thing that I work on. There are a lot of things done on different architectures for deep learning, using even normal deep learning, Bayesian deep learning, and convolution. I am not a deep learning person, so I am not familiar with all of those, but I know there's a lot of work going on is done in that area. And on the other side, many different flavors of trees. So I talk about isolation trees and random forests, but there are boosted blah blah blah. Many different ways of randomizing things and building and combining decision trees that are out there. Uh, there has been some attempts to use graph networks, but I don't remember if they were published or not. So that's more or less what I have in mind at this point.
Okay, thanks a lot. And that was nice that you mentioned also deep learning, because my second question, I think, mostly concerns this stuff. So the thing is that in some publication, we heard that probably now I mean the research society, and maybe not only research society, but a commercial society, is approaching to some performance wall or pay wall. I mean that in some situations, then you have a very complicated task. So it's very expensive to train some I think neural network in a proper way to achieve proper accuracy. And sometimes some commercial companies just first plan the training and then to reject this training. So my question is, have you ever met such a situation of pay or performance wall in your research?
No, because I consciously avoid it. But I think you are completely correct. That exists, and but I think and this is why I was stressing so much the formulation of the problem, because I think you are completely correct. But I also think that these big training issues occur when you have a lot of training data. Right. So first you have to have a lot of training data. Then you have the paywall problem, which you are completely correct exists. The problem in science is that I do not believe we have that much data for training, especially not in astronomy. So, and all of the things that I showed you, you said that I specifically stuck to very simple learning algorithms because I have a very small training sample. So I have like millions of light curves to classify, but we have a very small number of things that we can actually say with true that this is that class or the other. And so there is also in astronomy, there is a lot of things that happen, like people use simulations. So you do a simulation, you generate a lot of data with your simulation, and you train your machine learning model with your simulation, because then you can have as many data as you want because you are generating the data set. In this sense, yes, you might arrive in this problem that you found, that you told. But I do believe that it is, as I was talking before, this is there's a lot of faith on this about your simulator, and that the simulator is doing things that obviously agree with what's happening in the real data, which I think is a strong prior. So I have never encountered these problems, but I know they exist, especially for people working in academic public things. But I know they exist, but I consciously avoid them. That's why I didn't I
Okay,
didn't.
very clever. Okay.
Yeah.
Okay, thanks a lot.
No problem.
Okay. Are some more questions or no?
Alexei, we have, I think we have a question from Nadezhda Vasilyeva.
Yep, of course,
as I can see a raised hand.
Okay, Nadezhda, please ask your question.
Hello, everyone, and Emily, thank you a lot again for this very clear and interesting presentation. So I have a short question also, coming back to this uncertainty in input data. Yeah, to make clear if I understood right. So when you're when you're giving the suggestions of your system to as a result of unlabeled population, yeah, you give it to expert community. So are you waiting until the community comes to some consensus on what is it, or you gather different opinions? Because I'm working at in another field, it's a soil science. We also dealing, and we have a lot of attention to the opinions from the expert community on what is this, because different people can say really on the soil objects also different final, even the name of the soil. So how do you deal with this? You're really getting one label, or you assign some weights? And,
yes, this is a very interesting question. So there are two points here. First is the first classification exercise that I told you about, right? So in the classification exercise, things are pretty clear, because you ask for all of this was done in catalog data. So if you have the measurement, you know the class, there is no doubt about that, and then you just do the thing and continue training. That's fine. For the classification exercise, it's okay, because it's a well-defined mathematical problem, and the answer is well defined, right? So if it's a 1A, you observe a spectra, there is silicon, there is not, it's okay. I know that there are layers on this, but overall it's a yes or no answer once you have the observation. For the anomaly detection case, it's more complicated, because what happens was, from the beginning, as I said, in the first stages, we had two experts in our team, which was Maria and Lina, and we have a separated group of experts that were entitled to tell us if that thing was an anomaly or not. And I think maybe Alina will agree with me that we should have an odd number of experts for our next test, because sometimes it's very difficult to find to define what is an anomaly and what is not an anomaly. What we did was, for these specific works, we have we left them to decide, and they come to a conclusion, and then they reported it to us, and then the thing worked like that. For the purpose of the anomaly detection, I think that is enough, because what we wanted was only to provide the community with a list of possible interesting objects. So we are not saying this is this class or this is that class. We are just saying this might be interesting for the community, and we publish a list of things that might be interesting to people. At this point, this is how we are doing it. And in order to include, I think that what you are saying, you need more time in order to have a community consensus of what is interesting, of what it's not. You would need a longer time than we can afford for doing these exercises, these learning exercises. But just to end in a positive note, I don't want to be too much pessimistic here. Just to end in a positive note, I think that the good thing about this is that if at some point in the future you arrive to a community consensus about what is one thing and what is another, it's very easy to go back and just run the machine again with different answers. At least the way we implemented it, we have like log files that you can just change the log and learn and update again your state of knowledge. But at the moment you are developing the tool, you just have to do with whatever answer is possible, because a community consensus is really very difficult. I agree. Sorry, that was not an answer to your question.
Oh, thank you, Emily. Thank you.
Is anybody? No. Okay. So, Emily, thank you for your exciting talk, and for very promising talk about discoveries and about participation in LSST brokers and so on, and especially for transient discoveries. So we now, and I'm hoping that you will join to our conference in future, maybe for roundtable of discussion about machine learning, deep machine learning, and first result of LSST, and so on and so on. So about anomalies. So it is a place. Our conference is a place for discussion of your discoveries and method and approaches to astronomical problems. So thank you everybody for participating in the morning session. And now next session will start within 15 minutes. So please participate in our two astronomical sessions starting at Sergey, is it right? 12:30.
Yeah.
Okay. Yeah. Thank you. Bye-bye.
Thank you. Bye-bye. Thank you.